Okay, so today, thanks for coming, of course. Today I'm going to talk about the cache affinity solutions for virtual networking function or in general cloud workloads in OpenStack and Linux environment, okay? So this is a really complex topic. 150-minute talk I have to cover in in 15 minutes. So first of all, the agenda, I'm going to give a very short overview of the CPU cache affinity. Again, when I talk about cache in here, it's the hardware cache, okay, the CPU cache. Then we'll show a few graphs, like, what do you gain from the cache affinity, and then suggestion for possible extension to Nova to support cache affinity, okay? So first of all, some terms. The term environment, when I talk about environment, it basically means the compute host, the OpenStack, the host and guest operating system. And when I say conditioning of environment, it basically means tuning various parameters. That could be kernel, OpenStack, and various other parameters on the host, configuring or programming of the environment. When I talk about task, user, cloud admin and user, and the task basically at the VM, it could be container, vCPU, emulator, and other operating system on user space task, okay? So cache affinity, so what is that? If you don't know, now you know that certain cloud workload may actually benefit from the cache affinity, okay? Especially the virtual network function, media, cloud, especially the layer 1 and layer 2 cache affinity. Okay, so what is layer 1, layer 2 cache affinity? So look at the figure in here. So here you can see that there's a code there, which could be the hyperthread or logical processor, and then you have the layer 1, layer 2 cache there, and layer 3 cache. Layer 3 cache basically is shared by all the cores on a particular NUMA node. Layer 1, layer 2 may not be shared. They are not shared. They may be shared by the threads, hyperthread, for example, if there's hyperthread, right? And then, of course, you have the RAM. So the idea about layer 1, layer 2 cache affinity is that you want to keep the information on the cache or the cache line as much as possible, as long as possible. And if necessary, also, you should be able to share between various tasks. Like here, for example, you can see that there's a VM, vCPU. It has been loaded on a core. It's running on a core, and it may have also related tasks. Those could be user space processes or the kernel tasks that are related to the vCPU. You may want to run them on the same core to maximize the cache affinity. Give you an example. The network traffic is coming in. The packets may be processed by the kernel, for example, or the user space switch. And then it may be handed over to the guest operating system of the VM or VNF, right? And then from there, it may go to the user space of the VNF, right? From there, actually, it may go to another VNF that may be chained to that particular VNF. Now, the packet may contain information about the flow, right? So you want to keep it in a cache, let's say layer 1 or layer 2. And let's say that if your VNF is a firewall, and firewall has states, right? So, and stateful firewall. So the flow that came in, you may have to check it against the firewall state table, right? You are better off actually keeping both the flow information that just came in and the firewall state table, if not fully, but partially in the cache line, right? Layer 1, layer 2 especially. From there, it may go to another, VNF if you chain, right? So that's the cache affinity I'm talking about in here. And as you can see that the multiple tasks actually can share layer 1, layer 2. Then, cache affinity also can be achieved by various ways. Cache-aware coding, right? Cache-aware compiler optimization. Linux kernel actually is adding slowly, various kind of cache affinity-aware capabilities there, but they are mostly partial. Most of them are not virtualization-aware. But you can also achieve the cache affinity by tuning the environment. Right? That's what we are focusing on here. And you can do that from user space. Okay? Now, let me show you a few interesting graphs, what you can achieve when you actually condition a host for layer 1, layer 2 cache affinity. Okay? So here's the graph. So here you can see that a single host was actually partitioned into two parts. One is that you can see 6 cores are there that did not support the cache affinity, layer 1, layer 2, and 6 other core actually supported cache affinity, okay? Now, in order to condition a host with the layer 1 to layer 2 cache affinity is a very complex task. Let me put it this way first, right? But look at the graph now. At the top part, you see that the workload, the VNFs that ran actually on those 6 cores that were conditioned for layer 1, layer 2 cache affinity, just look at the graph. First of all, you see the improvement. There's like 20 to 25% improvement there. And also you can see the graph is so smooth, right? Look at the lower part. The variability is really bad there, right? I mean, you can see. So, but also you can see that same host we used to OpenStack extended flavor actually to run this 2 type of workload. But you can see the result there. Now let's look at the correlation to cache. This is another way of looking at the box. You see the variability. This kind of graph it shows, right? But now look at this. So at the bottom you see is the cache reference, layer 3 cache reference, meaning that the cores there, the cores that have been conditioned for layer 1, layer 2, they are making those references, right? So you make layer 3 cache reference because layer 1, layer 2, after the core basically misses the, layer 1 or layer 2, cache references, right? So again, you can see the number much lower. You also see it's very smooth, right? But look at the top. The variability is so much and also much higher than the cores what the workload ran with layer 1, layer 2 cache affinity, okay? Now, if you correlate that to KVM entry exit, again, look, lower and also very smooth, okay? So, this can actually tell you that, the various kind of workload actually can benefit from the layer 1, layer 2 cache affinity, especially the VNF and media workload. Okay, so so let's now talk about what kind of OpenStack extension we can provide to support layer 1, layer 2 cache affinity. Okay. Now, as I said, that conditioning an environment for layer 1, layer 2 cache affinity is very complex, okay? There are multiple different ways of doing that, and different ways actually provide you with different kind of result, okay? So now, of course, if you can simplify the procedure for layer 1, layer 2 cache affinity by providing cloud abstraction. So that's where the OpenStack comes in, right? So one way of providing the cache affinity layer 1, layer 2 is the vCPU pinning, right? That is already supported by OpenStack. In fact, there's a blueprint. It has not gone into the Liberty yet, but probably will go into the next version. So it's a good start, but further extension is needed. But I have to again emphasize is that vCPU pin is just one small part of the whole, procedure of environment conditioning, okay, to achieve a layer 1, layer 2 cache affinity. So ideally, we could actually provide OpenStack abstraction for the various level of cache affinity, but it may not be feasible time-wise and from technical perspective to actually add all those complex, the capabilities within OpenStack to support layer 1, layer 2, cache affinity. But we can at least provide some, the extension to OpenStack to actually simplify the, to simplify the procedure to apply to support layer 1, layer 2 cache affinity. Okay. So. Here is the OpenStack Nova, the vCPU pin blueprint. So what happens in, basically a few flavor extra specs have been defined. So when you deploy VM, you can specify these flavors. And when these, flavors are defined, the VMs are actually pinned to cores. And the cores are specified in a Nova conf parameter called vCPU pin set. Now, the core list that is in that set actually is a flat. It's not NUMA aware. It's of course not the layer 1, layer 2 cache aware. It's a flat list. So BCP pin basically can go and pick a random core, and if you want to have another, task to share the same cache line, then there's no guarantee that BCP pin is going to actually pick that core that is picked for the other task, right? So then, in order to provide the capability for that, we propose to actually partition the BCP pin set into multiple partitions. So as you can see in here, the experiment that we have run, there's 2 partitions there. One is layer 1, layer 2 cache affinity. One set, there's a set of cores there that has been conditioned to support layer 1, layer 2, and the other one was not conditioned, right? So if we can actually add that capability, then we should be able to actually pick the right set of cores to support that. Okay. The other thing is that as I said, that first of all, it's not NUMA aware, that core list. Second of all, as I said, that you have to also, when you deploy the VM, you should be able to tell Nova that, okay, when you deploy the next VM or next VNF, you pin it on the same core where another VNF has been pinned, right? I should be able to say that, or VNF or BCPU. So for that, it's very simple. Like Nova already has this capability called the hint the same host, meaning that an instance, when you try to deploy, it will be actually deployed on the same host of the instance ID. So simple extension, like, you can hint same core, okay, when you deploy, and specify the instance ID. Nova will figure out like which BCP has to be pinned on which core, right? Similarly, you can also specify like hint same NUMA node, instance ID, okay? So that's it, that's my talk, okay? So did I finish in 15 minutes?